Hey everybody. Today we're going to cover an algorithm for finding strongly connected components within a graph. It comes from Skiena's The Algorithm Design Manual. And what we're going to do is we're going to run his algorithm basically on this small example graph that he's given in his textbook. You can see from looking at this small example graph that he's kind of outlined the strongly connected components for us. Just a quick review: a strongly connected component of a graph is a section of the graph in which you can get to all of the other vertices of the graph within that sort of section. So for instance, from any vertex 1, 2, 3, or 4, you can get to any of the other vertices 1, 2, 3, or 4, right? If you started at 4, for instance, here, you could go, and you wanted to get to 3, you could go from 4 to 1, from 1 to 2, and then from 2 to 3. Strongly connected components are only relevant really on directed graphs, and this is a directed graph. Basically, we have a bunch of one-way streets. Maybe it could be two-way streets, but no two-way streets on this particular graph, all one-way streets. Okay, so we're going to run this algorithm, and to do so, I've made a small diagram that has a little bit more information on it than Skiena's diagram, including some of the variables that we need to keep track of in order to run the algorithm, the entry time for where we enter each vertex, entry t, DISC, which stands for discovered, and all of the vertices are currently not discovered, so DISC is false for all of the vertices. We have SCC, which stands for strongly connected component. That will identify the number of the strongly connected component in which this particular vertex resides. And then we have low. Now low is the oldest vertex that you can get to, or that resides in the same strongly connected component as the current vertex. So for instance, these four, which are all going to end up in the same strongly connected component, we saw it in the textbook just a second ago, low for each of these four will eventually be set to 1, because 1 will be the entry point for our algorithm. It will be the oldest vertex that is in this strongly connected component with these other four. All right, so over here we also have some global variables. We have components found, which tells us the count of the number of components we have currently found. We also have a time marker, and time will increase every time we enter or exit a vertex during our depth first search of the graph. And then we have this stack here that we call active, which we will use to keep track of strongly connected components in some way or another. Okay, so we begin the algorithm, strong components here. We have the declaration of this variable. It doesn't do very much. For int I equals 1 to the number of vertices, we initialize the lows to be I. You'll see that low in every case is the same as the number of the vertex initially as we start the algorithm. And the reason for that is that without knowing anything else, we assume that any individual vertex really is its own individual strongly connected component, and you can't get to any other vertices or get back from any other vertices from any given vertex until the algorithm tells us otherwise. And then SCC for strongly connected component for every vertex is set to -1 initially, which indicates that we have not yet found a strongly connected component for any vertex yet. Components found equals 0. Again, we found 0 strongly connected components at this point. And then we initialize the stack and initialize the search. We're not going to talk about those. And then we start our depth first search. Now, if this happened to be a graph that was a disconnected graph, it's necessary to run this loop here. Basically, you can just think of, in our connected graph situation, as running a depth first search on the first component, the first vertex of the graph, and that will do the trick without the loop. Okay, so we're going to run a depth first search starting at vertex number 1. All right, so in the depth first search, we increment the time by 1. And the entry time for this vertex is now 1. and this vertex has been discovered. Set it to true. After that, we execute whatever the process vertex early routine is for our particular algorithm. And in this case, process vertex early simply involves pushing the vertex that we are currently looking at onto the active stack. So vertex number 1 gets pushed onto the stack. After we process vertex early, then we start looking at all of the edges of the vertex. We process all of the edges, and we conduct depth-first searches if we discover any undiscovered nodes at the ends of those edges, right? Now there's only one out edge to examine here from number 1, specifically this one, which goes from 1 to 2, but if there were multiple, then we would do them in kind of numerical order. So for instance, if we were working on number 2, we would do vertex 2, 3, and then vertex 2, 4, and then edge 2, 3, edge 2, 4, and then edge 2, 5. But we're going to start with edge 1, 2 here. So we call the process edge routine. And the process edge routine is right here. First, we get an edge classification. We're not going to look at the code for the edge classification routine itself, but it classifies edges as either tree edges, and tree edges are to undiscovered vertices. So if the edge points to an undiscovered vertex, it's going to be a tree edge. It can also be a forward edge, it can be a back edge, or it can be a cross edge. For more details about forward, back, and cross edges, you can see earlier in Skiena's book. But we'll be interested in particular in back edges. We will have found a back edge whenever we have an edge that points back to an ancestor of our current vertex that has already been discovered. That's going to happen a little bit later on in the algorithm, and a cross edge will point to a vertex that has already been discovered in the graph, but isn't a direct ancestor of the current vertex. All right, so edge 1, 2 here is a tree edge because it points to an undiscovered vertex. Discovered equals false here. So because it's a tree edge, you'll notice we have if class, that is class of edge, equals back, we do some stuff. If class equals cross, we do some stuff. But we don't end up doing either of these things because we have a tree edge. So process edge does nothing for tree edges, which means in the future, every time I have a tree edge like 1, 2, I will just mention that process edge does nothing for a tree edge and move on. Okay, so the next thing that happens once we get to the end of an edge to an undiscovered vertex or a previously undiscovered vertex, we are going to mark that vertex discovered. And that is, we are going to mark discovered true. And we're going to conduct a depth-first search on that vertex, which involves increasing the time marker by 1, the time counter, and making the entry time to that particular vertex equal to the current time. From here, we process this vertex early. And again, the process vertex early function just pushes the vertex onto the active stack. And when I say process vertex early, that really just means process it, do this part of the processing before I look at all of the edges coming off that vertex. So after I've processed the vertex early, then I start looking at all the edges. The first edge I'm going to look at, because I'm doing them in numerical order here, is edge 2, 3. Edge 2, 3 points to an undiscovered vertex, right? So it is therefore a tree edge. Discovered is false, so it is a tree edge. And because it's a tree edge, process edge does nothing, right? If class equals back, we do something. If class equals cross, we do something. If class equals tree, we don't do anything at all. So we simply move on to a depth-first search, or rather we discover this vertex, mark it as discovered, and then we conduct a depth-first search of this vertex, which means we increment again our time counter by 1, goes from 2 to 3. The time of entry is now 3. And we are going to now process this vertex early, which involves, again, pushing it onto the stack, the active stack. Once we've processed this early, we begin processing its edges. It has only one out edge, 3 to 1. And this edge is now a back edge because the vertex to which it points has already been discovered. Discovered is true. It was the first one we discovered. So, and furthermore, this edge is a direct ancestor of this edge in our depth first search. We started here, then went here, then went here. So this is the grandchild of vertex 1. Vertex 3 is the grandchild of vertex 1. We have an edge pointing to a previously discovered ancestor. That's a back edge. So then we go check out in the process edge function what we do if we have class equals back. So if entry time y, and y is the vertex to which our edge points, in this case, vertex 1. Entry time for y, which is 1, is less than entry time for low x, and x is the vertex from which our edge is drawn, in this case, vertex 3. So low x, or low for vertex 3, is currently vertex 3 itself, right here. Low is 3. So entry time for 3 is also 3, and 1, entry time for 1, is less than 3. So when this happens, we assign low of x to be equal to y. So low of our starting vertex here is now set equal to the label of our ending vertex, which is 1. And we finish the process edge function because class does not equal cross. So we have now processed this edge. And because this vertex had already been discovered, we do not need to do a depth first search of it. So we have processed this edge. We come back to vertex 3 and look for any other edges from vertex 3, but there are no other out edges from vertex 3. So that means we're about to finish processing vertex 3 completely. Before we do that, we are going to process vertex 3 late. We're going to call this function process vertex late on vertex 3. So if low of vertex 3 is equal to vertex 3 itself, low is not equal to vertex 3 itself, it's equal to vertex 1, then we would pop components. We're not going to do that. If entry time for low of v, low of our vertex v is 1, and the entry time of vertex 1 is 1. So if 1 is less than the entry time for the low of the parent of v, that is the entry time for, this is the parent of our vertex 3, right? The low of that is vertex 2, because we never changed that, and the entry time for that low, which is this vertex 2, is also 2. So if the entry time here is less than this entry time here, which it is, then we set the low of v's parent to be the same as the low of v. So we set this, we set this to equal this. So I erase the low of v's parent and replace it with the low of v, which was vertex 3. And now we have processed vertex 3 late on our way out of the vertex in the depth first search. The last thing we have to do is to increment the time marker, because whenever we leave or enter a vertex, we increment the time marker. And behind the scenes here, we'd also, according to Skiena's implementation, have an exit time for each of these vertices. But the exit time is not used in this particular algorithm, so we didn't bother to write it down. But the exit time would be 4 in this case. All right, so we return to vertex 2 after having finished processing vertex 3. We had started by processing this edge, the 2, 3 edge of vertex 2, but we have to still continue processing the remainder of the edges for vertex 2. So we have to process vertex 2, 4 next. Now, vertex 2, 4 points to an undiscovered vertex discovered as false. Therefore, 2, 4 is a tree edge, and process tree edge does nothing. We continue to discover vertex 4, mark discovered as true, increment the time to 5, and the entry time for vertex 4 is now 5. Notice this is the first vertex where the entry time is different than the label we've put on the vertex. That will happen in a couple of other cases as well. Okay, then we have to process vertex 4 early. Processing vertex 4 early just consists of pushing it onto the active stack. And then we process each of the edges of 4, conducting a depth first search. So the first edge we process, again in numerical order, is 4 to 1. And this is a back edge again, because we are pointing to a already discovered vertex that is an ancestor. Again, it's the grandparent of vertex 4. Anytime we do that, it's a back edge. And in order to process a back edge, we check to see whether the entry time of the edge of the vertex to which the edge points, y, is less than the entry time of low of the vertex itself, the starting vertex. So low of 4 is 4, and the entry time for that is 5. And that's more than entry time for 1, the vertex to which our back edge points. So this condition evaluates to true, and we set low for our current vertex x, which is vertex 4, to be equal to 1, which is the vertex toward which this edge points. Okay. So notice that now all 4 of these vertices have low marked as 1, and that's no accident because they all fall in the same component as a strongly connected component as vertex 1 does, because from vertex 1 you can get to any of these, and from any of these you can get back to vertex 1. So you can get anywhere around this set of 4 vertices that you want to go. All right, so we have processed this edge, and we don't need to do a depth first search on vertex number 1 because it was already discovered. So then we continue processing the next edge of vertex 4, which in numerical order is 6 instead of 8. So we do the 4 to 6 edge. The 4 to 6 edge points to an undiscovered vertex. Undiscovered vertex means that the edge is a tree edge. When there is a tree edge, there's no processing to do for the edge itself, but we do mark the vertex discovered true. We increment the time marker to 6, and we note that the time at which we entered this vertex was 6. Then we process this vertex early. To do so, we place it on the stack. And then we proceed to process the edges coming out of this vertex. So the first edge coming out of this vertex that we are going to deal with, and as a matter of fact, the only out edge from this vertex is this one right here, which heads to vertex 7. Vertex 7 is also undiscovered, and therefore the 6 to 7 is a tree edge. So we do nothing for the processing the edge itself, but we do mark vertex 7 discovered. We increment the time marker again, and we make the entry time equal to 7. And from here we process the edge, we process the vertex, early, which means we push it onto the stack. And then we process the edges coming from 7, and again there's only one edge here, which points to 5. And 5 is an undiscovered vertex, so this is a tree edge. Edge processing does nothing. We mark the vertex as discovered. We increment the time marker again. We note that the entry time was 8. And again, notice that this entry time is different than the label on the vertex here, and that's totally fine. So then from here, we process we have to process this vertex early, which means we push it onto the stack. And then we go ahead and start processing the edges of vertex 5. And again, there's only one out edge from vertex 5. It points to 6. And 6 has already been discovered. And as a matter of fact, it was a direct ancestor of 5 in the depth first search tree. It was 6 was the grandparent of vertex 5, right? And so 5 to 6 is a back edge. We process it as a back edge. We check whether the entry time of the vertex to which our edge points, in this case 6, is less than the entry time of the low of the vertex from which our edge is pointing. The low is 5, the entry time here is 8, 6 is less than 8, so we set the low of our vertex number 5 to be y, the vertex to which our arrow is pointing, which is 6. Okay, now we don't have to do a depth first search on vertex 6 because it had already been discovered, which means we return to processing the vertices, the edges of vertex 5, and there are no other edges to process. So we are about to exit vertex 5, but before we do, we have to process it late. And we go check the conditions for processing a vertex late. If low v equals v, which is not the case for vertex 5, right? Low is 6 for vertex 5. And if entry time for low of v, now entry time for low of v, low of vertex 5 is 6, and the entry time for 6 is 6. So we're saying if 6 is less than the entry time for the parent of v's low, right? That is, if this 6 is less than this entry time right here, 7 was the parent of vertex 5, then we have to set the parent's low to be equal to our current vertex's low. So we have to set this guy's low to be this guy's low, which we do. And this is starting to make some sense because this is a cycle, right? And we can get from any one of these vertices in this group of 3 to any other of the vertices in this group of 3 by just following these arrows, right? The fact that the low is the same for each one of them is indicating to us that these are going to end up being in the same strongly connected component of the graph. Okay, so we were here. We've now finished processing vertex 5 late, which means we can now exit vertex 5, which means we increment the time by 1. And of course, the exit time for vertex 5 would be 9, but we are not noting that at the moment for this particular algorithm. And we return to processing the edges of vertex 7. So we had just processed this edge, finished processing this edge for vertex 7. There are no other outgoing edges for vertex 7, which means we're about to leave vertex 7, which means we process vertex 7 late. Go back to the process vertex late. If low of v equals v, 6 does not equal 7, so no, it does not. If entry time for low of v, entry time for 6 is 6, is less than entry time for the low of the parent of v, well, the low of the parent of v is also 6, so it's not less than, which means that we get to skip over this, and we have finished processing vertex 7. We increment the time marker as we depart from vertex 7 and return to vertex 6. So now we were in the process of exploring all of the edges from vertex 6. We just explored this outgoing edge, which is the only out edge from vertex 6. Therefore, we have finished all the edges for vertex 6, which means we now process vertex 6 late. If low v equals v, which it does in this case, low v does equal v, we are now going to pop component v. What does that mean? We come down here, we increment components found. Components found equals components found plus 1. So we found our first component that we are sure is going to be its own separate and distinct component. And we found it as we were backing out of our depth first search. SCCV equals components found. So strongly connected component for 6 equals 1. Our first strongly connected component. We will use the counter also as the label for our component. So component number 1 is going to be this group, and we're going to label it as such because it's the first component that's found as we back our way out. Okay. So then, but the idea is we want these guys also to be labeled as such, and here is where the stack comes in. So notice that the two elements sitting at the top of our stack are 5 and 7, which are exactly the elements that we are interested in being in this strongly connected component, right? So we come down here, we have while t equals pop does not equals v. So we first assign t to be the result of popping the first element off our active stack, right? And then we compare that to v. So we pop 5 off of our stack here. So now 5 is t in here. T does not equal our vertex, which is 6 that we are currently exiting. So we continue with this while loop here, and we set SCC, strongly connected component for t, which was 5, to be components found. So here's vertex 5. I set SCC to be 1. And then I continue with the while loop. Again, I pop another item off the stack here, pop 7 off the stack, set that equal to t, and t does not equal, 7 does not equal 6, which is our current vertex that we are leaving. So SCC for 7 is now set equal to components found, which is 1. SCC 7, 1. And then we return to the condition of the while loop. We pop another item off the stack here and set it equal to t. This item is 6, the last one that we want to include, and we have already actually marked it with the proper component. So we're going to pop the 6 off here, but now 6 does equal 6, which means the while loop terminates, and we do not execute this line of code. And we have successfully popped all components, and pop component was the last thing that we were going to do here in process vertex late, because the entry time for low of v is not less than the entry time for low of the parent of v. The entry time for 6 is 6, and the entry time for the low of 6's parent, which is 1, is 1. So 6 is not less than 1, which means we don't execute this as we are processing the vertex late. So finally, vertex 6 is fully processed. As we exit, we increment the time marker and go back to vertex 4. Now, vertex 4, we were in the middle of processing its edges. We'd processed this edge first, then we processed the 4 to 6 edge, and we still have one left to process, which is the 4 to 8 edge. So now we need to process this. The vertex 8 is undiscovered, so this is a tree edge. We do nothing for the edge processing itself. We do mark the vertex as discovered. We increment the time marker by 1. We set the entry time to be that time, which is 12. And then we process this vertex 8 early, which means pushing it onto the stack. And then we proceed to explore 8's edges. We have an edge going from 8 to 6 as our only outgoing edge. Now this edge is interesting. It points to an already discovered vertex. However, this vertex 6 is not a direct ancestor of vertex 8 in the tree. Because we started at 1, we came down here, we went over here, and then we backed out, we went over here, came down here and went around, then we backed out, and then went down here. So the only direct ancestors of 8 in the tree are 1, 2, and 4. 6 is not a direct ancestor, it's more like a cousin. So because it is pointing to an already discovered vertex that is not a direct ancestor of vertex 8 from which it comes, we mark vertex 8, 6 as a cross vertex. Then we go to check to see what we should do for processing a cross vertex. Interesting. If class equals cross, if strongly connected component of y, which is what we are pointing to, the edge is pointing to, is equal to -1, we're going to do some stuff. but strongly connected component of vertex 6 is 1, not -1. That is, we have already assigned this vertex to this strongly connected component of the graph. So we do nothing for this edge, and we return, and we don't have to depth first search vertex 6. We return to processing vertex 8. There are no more edges to explore for vertex 8, so then we're getting ready to exit vertex 8 and return to vertex 4, but we have to process vertex 8 late. So we go to process vertex late for vertex 8. If low v equals v, and lo and behold, it does for vertex 8. We are going to pop a component. So we come down here to the pop component. We increment components found. Then we set strongly connected component for vertex 8, our current vertex, to be components found. Components found is 2. We set strongly connected component of vertex 8 to be 2. It's going to be its own little separate strongly connected component from the rest of the graph. And then while t equals pop, while we assign, that is, t to be the result of popping the active stack, well, we pop the active stack and we get 8. Assign that to t. And 8, does that equal the current vertex? Why, yes, it does indeed. So this while loop does not execute at all, because 8 does in fact equal 8. So we are now done popping the component, and we return to processing the vertex late. If entry time for low of v is less than entry time for low of the parent of v, that is, if this vertice's entry time, which is 12, is less than this vertice's entry time, which is 1, then we're going to do some things, but it's not, so we don't do anything here, and we finish process vertex late for vertex number 8. We then return from vertex 8, but we increment our time in the process, returning to vertex 4. And we were exploring all the out edges of vertex 4, but now we've done all of them. We did this one first, and now we did this one, and now we have done this one as well. So we're about to leave exit 4 actually and return to vertex 4. We're about to leave vertex 4 and return to vertex 2, which means we need to process vertex 4 late. So we go over to process vertex late. If low for vertex 4 is equal to vertex 4 itself, it is not. Low of vertex 4 is equal to 1. If entry for low of v is less than entry time for low of the parent of v, so again, I look at the entry time for low of vertex 4. The entry time for vertex 1 is 1, and that is not less than the entry time for 4's parent's low. 4's parent is 2. The low of 2 is 1, and 1 is not less than 1. So I don't have to do anything here either as I process vertex 4 late, which means we are done with vertex 4. We increment the time marker as we leave vertex 4 and return to vertex 2. Okay, so we were in the middle of, way back in the day, we were in the middle of exploring all the edges from vertex 2. We have this edge, which we explored first. We have this edge, which we just finished exploring completely. And we still have this edge from 2 to 5. Now, 2 to 5 does not point to an undiscovered vertex, so it's not a tree edge. But it does not point, nor does it point to an ancestor of 2 in the tree. Instead, it points to a vertex that we can get to from 2 in the tree. That is, it points to a descendant of 2 in the tree, because we could get to 5 following our original tree path by going 2, 4, 6, 7, 5. So 5 is a descendant of 2. In this case, we say that this edge, 2 to 5, is a forward edge in the graph. And we go check to see what we do in forward edge situations. And the answer is nothing. We don't process this edge at all. And because 5 has already been discovered as a vertex, we don't need to do a depth first search on 5, which means we're done looking at this whole edge. And now we're done looking at all of the edges of 2. So from there, we process vertex 2 late. So we go look at process vertex late for vertex 2. If low of vertex 2 is equal to vertex 2 itself, low of vertex 2 is 1, not equal to 2. If entry time for low of v is less than entry time for low of the parent of v, well, they both have the same low, so the entry times will be the same. They are both 1. So again, we have nothing to do in processing vertex 2 late, which means we're going to leave vertex 2. We will increment our time as we leave vertex 2, and then return to vertex 1. We were in the midst of processing all of the edges of vertex 1. We started with this edge, and that is the only out edge from vertex 1, so we're done with the edges of vertex 1. Now we're about to leave vertex 1 and complete our algorithm, but before we can do that, we have to process vertex 1 late. So we process vertex 1 late. We say if low of vertex 1 is equal to vertex 1, and lo and behold, it is 1, 1. So we need to pop the component again. We come down here, components found, we increment in components found by 1. And then we set, we set strongly connected component for our current vertex, which is vertex 1, to be components found. Components found is, oh, sorry, I was supposed to increment components found, and I decremented it at set, So components found should be 3 here instead of 1. And now I set SCC to be 3. And then, while I can pop things off the stack and they're not equal to 1, I'm going to set the components of those things to be components found. So I'm going to sequentially pop things off the stack, starting with 4. And then I go over to 4 and set its low to be, its SCC to be 3, which is the current components found. And then I pop another item off the stack. I pop 3 off the stack, and I set its SCC, strongly connected component, to be 3 as well. I pop 2 off the stack and set its SCC to be 3. And then I pop 1 off the stack, but now I don't do anything in the while loop exits because 1 is equal to 1. Now that the while loop has exited, we return to processing vertex 1 late. And we did this portion of it already. The entry time for the low of v is not less than the entry time for the low of the parent of v. Here's, I think, a slight bug in the code because we can't actually go check out the parent of 1. There may have been a mention of this in the errata of Skiena's book that you can look at online. In any case, we can't evaluate this condition. We do nothing with it, and we have processed 1. We increment the time marker as we depart from vertex 1. We have now conducted our full depth first search. And because, again, we had a fully connected graph here, we don't really need to be concerned about this for loop, and our strong components algorithm is complete. So check it out. What did we get? We discover that each vertex has been assigned a particular strongly connected component. These 4 vertices were assigned strongly connected component number 3. This vertex was assigned its own strongly connected component number 2 because this vertex is off by itself. From this vertex, there are no other vertices that you can both get to and get back from if you're starting at vertex 8. So this is off by itself in its own strongly connected component. And then we have these 3 vertices in strongly connected component number 1. And that makes perfect sense because from any of these vertices you can get to any of the other 3. But if you leave this strongly connected component, or if you wanted to leave this strongly connected component, well, you couldn't, right? Because there are no out edges going to vertices from earlier in the graph within the strongly connected component. So these all have a strongly connected component of 1. Notice one more thing, which is that we set the strongly connected components as we were unwinding from our recursion. That is, as we were headed back out in our depth first search, that's when we actually set the strongly connected components. So the early vertices in the graph were labeled with strongly connected component number 3, even though we encountered these vertices very early in our depth first search. That's all.